Have you ever really stopped to think about the magic that's happening on your screen this very second? I mean, the data for this explainer, it's probably traveled thousands of miles to get to you, and it did it in like a blink of an eye. So how on earth does that journey actually work? Well, we're going to break it down.
All right, so to figure this out, let's just use this explainer itself as our test subject. It's sitting on a server somewhere, right? Could be thousands of miles from where you are. So how did it manage to cross entire continents, maybe even oceans, just to show up on your screen? That's the big question we're tackling today. So if I ask you to guess how data zips around the globe, what would you say? Come on, be honest. For most of us, the first thing that comes to mind is satellites, right? I mean, it seems so futuristic and logical. You just beam a signal up into space and then back down. But is that really how it works?
Okay, so on one side, you've got the common belief, satellites. And on the other, the surprising reality, a huge, sprawling network of undersea cables. And this right here is the key takeaway. The internet isn't floating around up in the sky. For the most part, it's actually living at the bottom of the ocean. Wild, right? So, you're probably wondering, what's the big deal with satellites? Why don't we use them? Well, it all boils down to one thing, distance, a lot of distance. These things are orbiting about 22,000 miles up in the sky. That means a signal has to go all the way up from a data center, hit the satellite, and then come all the way back down to you. We're talking a round trip of 44,000 miles. That is just a ridiculously long way to go.
And even traveling at the speed of light, covering that much ground creates a delay, a very noticeable one. It's what we call latency. And for things like streaming this explainer, or especially for online gaming or a video call, that little half-second hiccup is, well, it's a deal breaker. It is just way, way too slow for what we need.
Okay, so if satellites are a no-go, then what's the answer? It's time to pull back the curtain and meet the real hero of the internet. And it's not some wireless, magical cloud. Nope, it's a gigantic, physical network of actual cables, most of them buried underwater, that connect to the whole planet.
Just look at this thing. It's an incredible web of fiber optic cables, literally carrying our data as tiny pulses of light. This physical grid is what connects everything, from the data centers that are storing this explainer right now, all the way to the Wi-Fi router in your house or the cell tower your phone is talking to.
And the way they lay these things down, it's absolutely staggering. We're talking about special ships that literally drag a giant plow along the bottom of the ocean. It digs a trench, and the cable gets carefully laid inside it. These cables have to cross underwater mountains and deep-sea canyons. It is an unbelievable feat of engineering for sure. All right, so we've got the physical highways sorted out. The cables are the roads. But think about it. There are billions of devices connected to these roads. How does a piece of data, like a chunk of this explainer, leave a server in, Oregon, and know that it's supposed to go to your specific phone in London? It needs an address, right?
And that's exactly what an IP address is. It's the unique address for every single device that's online. Your phone has one, your laptop has one, the server holding this explainer has one. You can think of it as the digital world's version of a street address. And honestly, the shipping address analogy is perfect. A letter isn't going anywhere without a house number and a street name, right? It's the same for a piece of data. It needs an IP address. If it didn't have one, the information would just get completely lost in this giant network. It's the absolute core of how everything finds its way.
When you get right down to it, this whole system of unique addresses is what makes the internet, well, the internet. No IP address means no connection. Simple as that. It's the difference between mailing a letter to a specific person and just tossing it out the window and hoping for the best. But there's a problem here. A very human problem. IP addresses are just long strings of numbers, like 142.250.191.78. Can you imagine trying to remember that just to visit one website and then another one for another site? No way. Our brains are just not wired for that. There has to be a better system for us. And of course, there is a better system. It's called DNS, the Domain Name System. The easiest way to think about it is like a giant phone book for the internet. You remember the easy stuff, the names, like youtube.com. And the DNS does the hard work of looking up the number, the IP address, that the computers need. It's the perfect translator between us and them. And this whole thing happens so fast, you don't even notice it. It's literally milliseconds. You type in a website name, your computer instantly asks a DNS server, hey, I need the number for this site. The server finds it and sends it right back, and boom, your browser uses that IP address to connect. It's so simple, so elegant, and crazy fast.
Okay, let's recap. We've got the physical roads, the cables, and we've got the addresses, the IP and DNS system. So now let's talk about the actual cargo. How does a big file, like this HD explainer you're watching, get from point A to point B without clogging up the whole system? Well, here's the secret. It's not sent all in one big lump. Instead, the entire file is chopped up into thousands and thousands of tiny little pieces called packets. And sending the data in these small, bite-sized chunks is exactly what makes the internet so incredibly efficient and reliable.
So what's inside one of these packets? Well, you've got a small piece of the actual data, a tiny bit of this explainer. But just as important, it has a digital shipping label slapped on it. This label has the from address and the to address, the source and destination IP addresses. And crucially, it also has a number on it, telling your device where this specific puzzle piece goes. And this is where the real genius of the internet comes in. Get this. The packets don't even have to travel together. Each individual packet zips off and finds the absolute fastest route available at that very second. They might take different paths, they might get stuck in a little traffic, they might arrive all jumbled up and out of order, but it doesn't matter because your device just looks at those sequence numbers and puts the whole thing back together perfectly, so you can watch this explainer without a hitch. Okay, we've got the cables, we've got the addresses, and we've got the packets. But for this whole crazy, complicated global thing to work, for it to not just completely fall into chaos, there's one last invisible ingredient we need. And that's a common set of rules for everyone to follow. And those rules are called protocols. A great way to think of them is like the grammar of the internet. They're the agreed-upon rules for everything. How to format a packet, how to write an address, what to do if a packet gets lost. It's what ensures that a phone made in Korea can talk to a server made in California. They're all speaking the same language. Think back to our postal service analogy. Imagine if every city had a different way of writing an address. Letters would never, ever get where they're going. It would be total chaos. That's what the internet would be like without protocols. They are the essential, fundamental agreement that keeps the entire system from falling apart. So there you have it, the incredible journey of this explainer. From a server down into a fiber optic cable at the bottom of the ocean, chopped into thousands of packets, each one guided by an IP address and a DNS lookup, and the whole dance is orchestrated by a shared set of rules called protocols. It's a global machine built on amazing physical engineering, and maybe even more importantly, on a system of trust and cooperation. Which leaves us with one last big question to think about. What happens when the rules of that machine are bent, or even broken?